Дозвольте, я тоді надам слово іншому доповідачу. Інший доповідач – це якраз мій учень Олександр Петрович Довгопятий з доповіддю on the possibility of joining two part of points in convex domains using path. Прошу, будь ласка, Олександр Петрович, вам слово.
Okay, thanks. First of all, let me to introduce myself. My name is Dovhopiatyi Oleksandr. I am PhD student of Zhytomyr Ivan Franko State University. And the topic of my report is on the possibility of joining two pairs of points in convex domain using paths. First of all, I want to thank all organizers and all people who participate in this conference for such an interesting opportunity to present my results. And results of my research are one theorem and two consequences, which I want to present you today. And I want to explain an idea how this theorem can be proved. And I want to note that the similar results were obtained for a domain, which is unit ball, by my scientific supervisor, who is our chairman for today, by the way. And let's start from theorem 1. Let's recall that set C is a convex if we can join any 2 points of C. We can join by segment, which belongs to C as well. We define the Euclidean distance between sets and Euclidean diameter by the next formula, as usually. As usually, we will set ball centered at point x0 with radius r as b x0 r. And we will set sphere centered in points x0 with radius r as s x0 r. Let's see a theorem which was proved. Let D prime be a bounded convex domain in Rn, and let B be a ball centered in points y star, which belongs to our domain D prime, with the radius which is equal to distance from this point to the boundary of this domain divided by 2. And let's Z0 is a point of boundary on our domain. In this theorem, it was proved that for any point AB, which are close enough to point Z0, we can find constant C0 such that distance between segment AC and BD more equal that than distance between points AB multiplied by this constant. Oh, sorry, I think I forgot to say that we can find points AB from the closure of this ball centered in points y star and with radius which is equal to distance from this point to the boundary of this domain divided by 2. To prove this theorem, I divided the process of proof into 3 different cases, and let me explain what cases I mean. So in this theorem, we have domain D prime, which is bounded and convex. We have points y star, which belong to this domain, and we have ball centered in with center y star and radius which is equal to distance from this point to the boundary divided by 2. So this ball is completely belonged to this domain, except that we have point Z0 from the boundary, and we have points A and B which are close enough to this point. We want to prove that we always find points C and D from the closure of this ball, such that distance between segment A, C, and BD more equal than distance between points A and B multiplied by some constant, which depends on diameter of this domain and distance from this point to the boundary. I want to note that the angle between vectors A y star and AB can be less than pi divided by 4, we will call such angles as small angles. These angles can be more than pi divided by 4, but less than 3 pi divided by 4. And we will call such angle as large angle. And this angle can be more than 3 pi divided by 4. We will call such angle as very large. There are exactly these three cases we will discover separately to prove this theorem. And let's start from the first one, which is the easiest one. When this angle is large. So this angle is more than pi divided by 4, but less than 3 pi divided by 4. We can draw a segment from the point B, which is parallel to segment A, y star, and has the same length. We can prove by the triangle inequality that the end of this segment belongs to our ball 2, and we can denote C as y star and D as the end of this segment. After that, we need to estimate distance between segment AC and BD, and it's very easy to do. For example, from this triangle. Any further, we will denote distance between points A and B as epsilon 0. So distance between these two segments, AC and BD, equals to sine of this angle multiplied by distance between point A and B. But I want to recall that now we have case when this angle is more than pi divided by 4, but less than 3 pi divided by 4. So sine of this angle more equal than square root of 2 divided by 2. As we see, we can set C0 equals to square root of 2 divided by 2 to satisfy inequality 1. This inequality. Unfortunately, other cases aren't so easy as first. It's obviously because we cannot use the same method, for example, for a case when this angle is small, because sine of such angle can be close to 0 as much as possible. So we will need another method. Let's see at figure number 2. Now we will talk about case 2 when we have small angle. So such angle that's less than pi divided by 4. We will draw orthogonal to A y star, and we will denote by X double star and Z double star points of intersection of this orthogonal with boundary of our circle. Except that we will denote X0 and Z0 as middle of this segment. And we will join point A with point X0. After that, we will draw a segment through the point B, which are parallel to A X star and has the same length. We can prove again that the end of this segment belongs to our circle, centered at points y star. After that, to estimate distance between these two segments, we will need some geometry, some properties of trigonometric function. So I will show you only the final result. I'm so sorry, I forget to say one important thing. In this case, we denote C as point X star and D as the end of this segment. We can do it because the end of this segment belongs to this ball too. We can show it by in triangle inequality. So using some properties of trigonometric functions, we can estimate distance between these two segments. We can estimate that this distance more or equal to distance between points A and B multiplied by this expression. So we can denote C0 as this expression to satisfy theorem 1. And the last case, when we have very large angle. So we have such angle that's more than 3 pi divided by 4. Let's see at figure number 3. We will do something very similar to what we did in previous case. We will draw an orthogonal to A y star. We will denote x double star, z double star, x star, and z star at the same way, but we will join point A with z star, and we will draw a segment through the point B, which are parallel to A z star and has the same length. And we can show again that the end of this segment belongs to our ball. After that, we will denote point C as Z star and D as the end of this segment. We need to estimate distance between between such segments again, and we can do it using geometry, properties of trigonometric function again. I will show you only the final result for the last case. We can estimate that distance between these two segments more equal than distance between points A and B multiplied by this expression. So we can set Z0 so we can set Z0 equals to this expression to satisfy theorem 1. Of course, for all three cases, we have different constant. So to find a constant which satisfies this theorem for any case, we should take a minimum value of all numbers which we received earlier. And this ends the proof. Except that, I want to show you some consequences which we can receive by this theorem. Let's recall something. Let's recall that a Borel function rho is called an admissible for a family gamma if the relation 18 is true for any locally rectifiable path from this family gamma. A modulus of gamma is defined at 19, and the following statement holds. Let's under conditions of theorem 1, gamma denotes the family of all passes that join the segment AC and BD in D prime. Then inequality 20 is true, where M is the modulus of family of passes defined in 19, and M of D prime denotes the Lebesgue measure of D prime. And 0 is this constant from theorem 1, which we received earlier. It's easy to prove using theorem 1 because we can take such a function. Using theorem 1, we can prove that this function is admissible for a family gamma. After that, by directly substitution this function in the integral in 19, and by the definition of affinium, we can receive inequality 20. And except that, I want to show you a second corollary. Let's, under condition of theorem 1, gamma denotes the family of all passes join the segment AC and BD in D prime. Then inequality 21 is true, where M is the modulus of family of passes defined in 19. Cn is some constant depending on the n and d prime. To prove that, we will need to use some material from the books, which are included in references of this article. For example, we will need such formula, except that m defined as follow. And by the triangle inequality, we can show that diameter of segment AC more or equal than 3 delta star divided by 8. And we can do it in the same way for a diameter of BD. Using it, we can estimate modulus of this family. We can receive inequality 23. And except that, I want to recall some other definitions. A domain D is called a domain of the quasi-extremal length if inequality 24 is true for a finite number A0 star, which is more or equal 1, and all continua E and F in D. Except that we can observe that D prime is a John domain because our domain is bounded and convex. Thus, D prime is a uniform domain using some other material because convex John domain is uniform. And using some other material, we can observe that this domain is a domain of quasi-extremal length because uniform domain is a domain of quasi-extremal length. Now we should use inequality 24 and inequality 23 to combine them. After using it, we can receive inequality 25, where where this constant equals to Cn divided by A0 star. So that's all that I wanted to present you. Thanks a lot for your attention.